Good morning, everyone. My name is Xin Chen. Today I will present my work title Improve Dynamic Performance of PMSM Drives Using Bandwidth Turn IP Speed Control. This will focus on the speed control of a permanent magnet synchronous motor drive. The main purpose is to improve the response speed of an IP speed controller while keeping it low overshoot characteristic. The presentation is organized as follows. First, I will introduce the motivation and the main problem. Second, I will explain the PMSM FOC structure and the speed loop model. Third, I will describe the delay-aware PI baseline design. Then I will introduce the bandwidth turn IP speed controller. Finally, I will show the experimental result and give a conclusion. PMSM drives are widely used in applications that require high efficiency and fast dynamic response. For speed control, the conventional PI controller is still widely used because it is simple and easy to implement. However, the PI speed controller has one important issue. Its common response contains a controller zero. This zero can make the response faster, but it may also cause overshoot. Join speed command change. To reduce this overshoot, the IP controller can be used. The IP structure can reduce the zero-induced overshoot effect. However, if the IP controller directly reuse the PI design parameter, its response becomes much slower. Therefore, the main problem of this study is how to improve the response speed of the IP's controller while keeping its low overshoot behavior. So this figure on this side show this basic difference. The PI response is faster, but it has overshoot. The IP response is smoother but slower. In this study, we use FOC structure. The interloop is the current loop. It controls the torque production current, which is the Q-axis current. The outer loop is the speed loop. It generates the current command based on the speed of zero. So the speed loop mentally determines how fast the motor follows the command. In this work, we focus on the design of the speed controller, especially PI and IP controllers. In the simplified model, the speed command goes into the controller. The controller outputs the current command. This current produces torque through the motor constant. Then the mechanical system converts torque into speed. For the speed loop design, we do not ignore the current loop. Instead, we approximate it as a simple first-order system. It means the current loop behaves like a system with a constant response speed. The mechanical part of the motor is also simplified. It converts torque into speed, and its behavior depends on the inertia. So the overall speed loop plan includes both the current loop dynamic and mechanical dynamic. In real systems, there are also delays. These delays come from sampling, computation, and filtering. We combine all these effects into one equivalent delay. This delay will be considered in the controller design. Next, we design the PI controller as a baseline. We choose 3 design speed for compression: 40, 50, and 60 radians per second. The controller gens are not chosen randomly. They are calculated based on the desired response speed and the system delay. One important point is the PI controller introduces a zero in the system. This zero can help speed up the response, but at the same time, it may cause overshoot when the speed command change. This is why we later consider the IP controller. In this study, we compare 3 cases. The first one is the PI controller. It gives a first response, but it may have overshoot. The second one is IP1. It uses the same parameters as the PI controller. It can reduce overshoot, but the response becomes slower. The third one is IP2. This is the return IP controller. It is designed to improve the response speed while keeping low overshoot. In simple terms, the IP structure reduces the effect of the zero, so response becomes smoother. But if we do not return, it will also become slower. To solve the slow response problem of IP1, we use a bandwidth-based returning method. First, we design the PI controller and make sure its actual bandwidth. Then we adjust the IP controller. The goal is to make its bandwidth close to the PI case. We keep turning until the difference between the two bandwidths is small enough. After this process, we obtain the IP2 controller. So IP2 is designed to match the real performance of the PI controller, not just its original design volume. The proposed method is tested on a PMSM drive system. We use control structure with real-time implementation. The motor speed is measured by an encoder. The main conditions are as follows. The DC voltage is 160 volt. The switch frequency is 10 kHz. The sample time is very small, allow fast control. The speed command is a step signal. It increases from 0 to 500, then 1000, and finally 1500 RPM. All controllers are tested under the same condition. This slide shows the comparison of bandwidth. We can see that IP1 has a much lower bandwidth than PI. For example, in a 50 radians per second case, PI achieves about 10 radians per second, but IP1 is only around 2. This explains why IP1 is much slower. After returning, IP2 increases its bandwidth, and its volume becomes very close to the PI case, so IP2 successfully recovers the lost bandwidth. This slide shows the main experimental result. The PI controller has the fastest response, but we can see a small overshoot. IP1 has no overshoot, but its response is clearly slower. After returning, PI2 becomes much faster than IP1. At the same time, it still has no overshoot. In terms of performance, IP2 reduced the rise time by about 70%. and also reduce the settling time by a similar amount. So IP2 achieved both fast response and low overshoot. In conclusion, the PI controller is fast but makes overshoot. The IP controller can reduce overshoot, but it becomes slower if not properly tuned. By using bandwidth-based returning, we designed the IP2 controller. The results show that IP2 improved the response speed while keeping a low overshoot. In potential design, we should consider both speed and stability instead of focusing on only one factor. Thank you for your attention.